Hello, everyone, and thank you for attending this session. My name is Rebekah Hauser, and on behalf of my colleagues, I'm delighted to present our work, A Comprehensive Measurement-Based Investigation of DNS Hijacking. So just to give an idea of what we'll cover, we'll start with some background on the DNS and then discuss our measurements of domain hijacking attacks. I'll briefly discuss our experiment in detecting domain hijacking, then wrap up with a discussion. The DNS is essentially a directory that takes questions about names such as example.net and returns information about those names. In a DNS hijacking attack, the adversary is able to trick users into accepting incorrect answers to questions about where to find a domain or information about a domain. DNS hijacking attacks come in a few different flavors. To help clarify the difference between these, it's helpful to keep in mind the process by which the DNS is used to retrieve information. This process, known as resolution, starts when a client called a stub resolver sends a query to a server called as a recursive resolver. The stub resolver is usually running on an end user's device, and the recursive resolver is often a server provided by an ISP or enterprise. The recursive resolver will first check its own cache to see if the answer to the user's query is in the cache. If the answer is not found, the resolver will start to query a set of authoritative name servers. The recursive resolver will start with a query to a root name server. The root name server will not actually give an answer to the query, but will instead return a referral to a top-level domain or TLD name server. The recursive resolver will then send the same query to the TLD name server, which will likewise respond with a referral to the authoritative name server for example.net. The resolver will then send the query to this authoritative name server, which will finally return the answer to the original query. And the recursive resolver will finally return this to the user. Note that this process involves several components controlled by various groups. Queries and responses may traverse many networks around the world during the resolution as well. And this distribution allows attackers a variety of options for executing DNS hijacking attacks. And I'll next review a few of the more common approaches for these. One approach to completing a DNS hijacking attack is off-path spoofing. With this approach, the attacker cannot see or directly interfere with messages between a recursive resolver and the authoritative name servers, but can send queries and responses to the recursive resolver. In this scenario, to get the resolver to accept a bogus response, the attacker has to send responses in which it guesses certain values that the resolver expects to see in the response header. The attacker has to first prompt a recursive resolver to send queries for a domain to be hijacked, then flood that resolver with spoofed responses that appear to come from an authoritative name server. A second approach to DNS hijacking is a man-in-the-middle attack. In this case, the attacker controls part of the infrastructure that DNS messages traverse between a recursive resolver and authoritative name servers. The attacker can view, block, and replace messages directly. Finally, with domain hijacking, the attacker is able to change the records indicating a domain's authoritative name servers and have them point to its own servers, or control direct responses directly from the domain's legitimate authoritative name servers. Attackers can accomplish a domain hijacking by compromising the target domain owner's account with a third party, such as a registrar or DNS management service, or by taking advantage of vulnerabilities in the registrar provider to gain control of a domain's DNS. Domain hijacking in particular drew our attention. First, we found that this type of attack hasn't been studied as closely as other types of DNS hijackings, so relatively little is known of their expected or actual characteristics. Second, several prominent attacks in the past few years have highlighted these as a serious and potentially growing threat. These incidents include Angler, Spammy and Sea Turtle. In the case of Angler, attackers used thousands of hijacked domains to distribute malware. Similarly, Spammy leveraged hijacked domains to send spam emails. These included bomb threats that led to multiple building evacuations. Finally, Sea Turtle was a nation-state-sponsored espionage campaign that targeted several governments as well as private organizations. The Sea Turtle attack especially captured attention and highlighted how the DNS could be leveraged for international cyber warfare, and raised concern that this could lead to similar attacks in the future. Various defenses against DNS hijacking attacks have been created. Foremost among these is DNSSEC. Others include using registry locks or simply following best practices for keeping systems secure and up to date. Unfortunately, these measures are not always deployed, and even when they are deployed, they are often not correctly implemented. Some approaches to domain hijacking detection proposed in previous works have involved comparing past DNS records used by a domain with new records to evaluate whether the characteristics of the previously used and new resources are similar. One system relied on a few simple checks that basically looked for any changes in name servers or IP addresses. Since changes within the DNS happen relatively regularly, this is not a particularly scalable approach. Another system was designed specifically for domains using content distribution networks, and it's not clear how the proposed approach would work for other types of domains. Further, both this and the last work listed here focused on characterizing newly seen IP addresses. Given a trend towards increasing centralization in the internet that leads to many domains to use hosting providers, which attackers can also access, we believe that going forward it would not be wise to rely so heavily on the characteristics of IP addresses. Thus, while we drew on these works to inform our own approach, we concluded that none provided a particularly promising framework for domain hijacking detection, and more work is needed in this area. In order to understand how domain hijackings may be detected, we of course need to first understand the characteristics of those attacks. Thus, we started out by searching previous research and news stories for accounts of these incidents. From our search, we identified 34 accounts of confirmed domain hijacking attacks. These divided nicely into a few categories based on the apparent motives of the attackers. Most of these incidents involved activism or mischief and were generally defacements, usually of popular domains. Some of the attacks evidently provided direct financial gain to the attackers, while others, such as Angler and Spammy Bear, were used to distribute malicious content. Finally, two, including Sea Turtle, were used to collect information. From the reports of the attacks, we obtained over 27,000 indicators of compromise or IOCs. These included the fully qualified domain names, FQDNs, known to have been targeted in the hijackings, as well as the name servers and IP addresses used by attackers. We used these IOCs to search a passive DNS dataset for evidence of the attacks. To give an idea of the dataset with which we were working, some background on passive DNS or PDNS is helpful. PDNS replication is a technique used to capture and store DNS responses. The typical flow of the data starts with the sensors, which passively collect DNS responses between recursive resolvers and authoritative name servers. The sensors pass the data to the analyzers, which extract relevant fields to send to the collectors. The collectors finally update the database, and the query processors allow users to access the database. We obtained our PDNS dataset from Farsight Security. Again, to give an idea of the data we were using, it's been collected from a global network of sensors and from zone files courtesy of ICANN. And this collection process has been happening over the past 10 years, and as of the end of 2019, the database contained over 130 billion sets of records with data for over 51 billion fully qualified domain names. To clarify some of the following discussion, it's also helpful to see the basic anatomy of the PDNS records we used. The first three fields were taken directly from the captured DNS response. The R name field contains the name of the resource requested in the original query. The R type field indicates the type of resource requested, and the R data field includes the response. The next three fields are added by the tools creating the DNSDB. The first and last name timestamps indicate the first and last times input to the PDNS database captured the given response, and the count indicates the total number of times this response was seen in the input. We use the passive DNS data to examine various characteristics of the attacks, including attacker infrastructure, the appearance of new FQDNs within the records for hijacked domains, and the types of records that attackers changed. When considering attacker infrastructure, we checked the autonomous systems that attackers used. We found that attackers did not seem to favor any particular group of system, as most were used on only one attack. As only 6 out of the 89 autonomous systems used by attackers in the hijackings that we studied appeared in more than one attack. One interesting pattern that appeared in attackers' use of infrastructure was that of shared hosting. That is, attackers use the same machine to host both a malicious authoritative DNS server and a proxy or web server. You can see an example of that here in the records showing evidence of attack on the New York Times domain and nytimes.com. The two name servers shown here, ns1 and ns2.syrianelectricarmy.com, are attacker name servers. Note that both these and nytimes.com resolved to the same IP address during the attack. Unfortunately, using this pattern of shared hosting cannot simply be taken as an indication of malicious activity in all cases. When we investigated the records for the hijacked domains that we studied, we observed many apparently legitimate cases of an FQDN resolving to the same IP address as its associated name servers within an overlapping period of time. Thus, the pattern of shared hosting is not necessarily suspicious, although it is interesting, and may merit further investigation to understand if and how it could be used to detect a hijacking. We also noted some interesting patterns in the appearance of new FQDNs queried in the A records for a domain. Over 4,200 A records showed evidence of attacker activities, that is, an attacker IP address in the R data field. Of these, about 45% included a name that had already appeared in previously seen A records. Almost the same amount, though, about 44%, appeared before the attack only in CNAME records. In most cases, CNAMEs previously used in resolving the given FQDN were in other domains, that is, domains outside of the attacker's control. To give an illustration of how this works, suppose demo.example.net has a CNAME record pointing to example.com. If an attacker hijacked example.net but not example.com, the attacker could not control the traffic associated with demo.example.net if continuing to use that CNAME record. By responding to queries for the domain demo.example.net with an A record containing the IP address of the attacker's own server, the attacker can maintain this control. Of course, this is not the only option available to the attacker, and not all cases of CNAME replacement followed this pattern. However, it was sufficiently common that we would consider it worth examining and trying to detect domain hijacking. For those instances where the FQDN in the RNA field of A records indicating hijacking had not previously appeared in any records, we checked the reasons. Most of these cases were related to an attack on Craigslist. The domains Craigslist.com and Craigslist.org were hijacked in November of 2014, and the A records of the domains on the day of this attack showed the appearance of a wildcard record, which the attackers presumably created. The use of a wildcard record suggests that while the attackers wanted to make sure that they received all the traffic directed to the hijacked domain, they were not sure what queries to expect. The wildcard record appears to have caused a significant spike in the number of new A records seen for the first time that day, as illustrated here. The surge was mainly due to the appearance of queries for domains that appeared random and created algorithmically. While the source of these queries is not clear, it seems possible that such queries did exist before the date of the attack and received NX domain responses, which do not appear in the passive DNS dataset we used. Once the wildcard record was in place, queries for these domains would have received an A record in response, thus inflating the number of new A records captured by the PDNS sensors that day. In any case, both the appearance of the wildcard record and the change in the DNS resolution patterns could be helpful indications of an attack. While the ultimate goal of a domain hijacking is to redirect users to new servers, which generally involves changes in type A records, in many of the DNS hijacking attacks, we noted that multiple record types were changed. To analyze patterns in these changes, we divided the records into groups based on the date of their first seen timestamp. For this, we excluded the domains targeted in the Angler and Spammy VR campaigns, as these had somewhat unique characteristics. For the remaining attacks, we found records belonging to 55 hijacked domains appearing on 81 attack dates. Here we can see the record type groups for attack dates and dates on which no attack is known to have occurred. We see that most attacks tended to manifest themselves in changes to multiple record types. While over half the changes on non-attack dates involved changes only to A or quad A records, a large portion of changes on attack dates involved NS, CNAME, MX, and SOA records as well. Checking the new MX and CNAME records showed that these were often used to point mail and popular subdomains such as www to the apex domain whose IP address had already been changed by the attackers. This type of pattern is similar to what we saw with the CNAME records and its consolidating power. Also, the preference for new MX records was sometimes changed to 0 or highest priority, even when that preference may never have been used before in the domain's MX records. Finally, we noted the prevalence of the change in NS records on attack dates. While this pattern is expected, given that domain hijacking by definition involves a change or taking over a domain's name servers, it is worth highlighting. As seen here, changes in NS records are generally relatively rare, so focusing on assessing these changes is a potentially promising or efficient approach to detecting domain hijacking. Having gained some insight into the dynamics of domain hijacking attacks, we wanted to test our ability to use these insights for domain hijacking detection. We recognize that domain hijacking detection is likely to require active measures extending beyond the DNS in some cases. So our primary goal here was to examine if detection based on passively connected DNS data could be used to flag at least some DNS hijacking attacks and reduce the need for potentially expensive active probing in general. Regarding our threat model, we wanted to explore defenses that would be useful for a party such as a network operator, our defender, attempting to determine if DNS responses entering a local network represent a domain hijacking. Such a defender would have access to DNS responses between a recursive resolver and authoritative name servers. Thus, the system we considered would take these responses as the primary input. The first step in the system would filter out incorrectly formatted or invalid responses. The next stage, augmentation, would focus on A records, adding information about the organizations and countries associated with an IP address. After feature extraction, the classification module would produce a list of flagged responses for further investigation. In our design, an instance to be classified comprises all the new records for a given domain on a given day. The statistics of this group of new records are extracted and then compared to statistics on previous days in order to obtain features. We used 20 features total of this sort. To test our system, we ran a set of simulations using PDNS data. That is, we replayed the PDNS data through the system using timestamps in the records to determine in what order records should appear. For the experiment, we used PDNS data for several domains in addition to those known to have been hijacked. These included the Alexa Top 100, as well as domains and categories corresponding to those we saw frequently in our study of hijacked domains. For the classification portion of the system, we tested random forest and SVM classifiers. For evaluation, we split the data set by date of the firsting timestamp into different groups, then used tenfold cross-validation with each group separately. The decision to split the data this way was motivated by our understanding that DNS dynamics have changed over time, and trying to assess changes in one period based on data from a much earlier or later period would be unreasonable. First thing to note here was that the false positive rate was very low, which is essential for this type of system. However, the recall was also not so great. While it was relatively high in some tests, or very high in some tests, the results were worse than those of a random guess than others. The results in this last case were largely due to instances related to sea turtle. Due to the length of time over which that attack was executed, and the way in which the PDNS data is deduplicated, we believe we are losing some information about the timing of new records that would be helpful to identify changes. In a live environment, the dynamics could be more clear, which could improve the recall in this case. And that brings us to our final summary of our work. First, a note regarding limitations. The PDNS data was wonderful in that it allowed us to work with data for real attacks. However, it did not allow us to see how well our approach to detection would work in real time. Understanding this would require further testing in a live environment. Further, attackers could potentially evade our approach by using popular third-party providers, particularly those operating DNS management services. If the victim is also using the service or the service is generally trusted, then detection could be very difficult and may have to rely on indicators outside of the DNS. To summarize our findings, changes in DNS responses do provide key indications about whether a domain hijacking has occurred. This information can be leveraged to build a lightweight filter based on passively collected DNS data prior to initiating more resource-intensive investigations. Also, the authoritative name servers in particular provide important insights, and developing more nuanced features or filters focused on these is a promising area of future work. I'd like to express thanks to our reviewers for their input, also to those who provided support for our research, and to Farsight for providing our data. And thank you all for your time.